we can. Well, why don't we just plan to briefly connect after your talk, just because we were talking about arranging visits next week and so on. So maybe we could just have a quick chat after.
Sure.
Yeah. Anyway, thanks so much for coming. It's great.
Okay, thank you for having me.
Yeah, sure. Okay, I think we have our audience has now come in. So good afternoon, everyone. Good afternoon, everyone. I'm very happy to introduce today Mark Zelinka, Dr. Mark Zelinka from Lawrence Livermore National Laboratory. He obtained his PhD from the University of Washington in 2010, and since that time he's been leading an active research program there, first as a postdoc and now as a research scientist. And his career thus far has been marked with awards in recognition of his achievements in early career research, for excellence in publication, and for outstanding mentorship service. Mark's coming to us as a climate scientist whose research is breaking new ground in our understanding of climate sensitivity. This is the amount of global warming we expect for a given amount of greenhouse gas emissions. And this is critical work providing great insight into how warming is controlled by clouds, by radiative forcing, and other feedbacks. I'm really looking forward to hearing from Mark at this time. This is kind of a critical time for this research as this new crop of models has come on stream. And it's bringing lots of questions with it, some surprises, and perhaps some concern. And so as a predictive science, I think it's really important for all of us to hear what the underlying reasons are and what we should learn. So I'd like to welcome Mark. We normally have a round of applause, so consider yourself applauded. And I really appreciate your coming to share this with us today.
Thanks a lot, Paul. I really appreciate the invitation to present here and for the introduction. As Paul alluded to, yeah, we have a whole new set of global climate models that have just submitted their results from a large coordinated group of experiments. And I will try to convince you that these models are now showing larger climate sensitivity than their predecessors that have done the exact same experiments. And so the first part of the talk will be in trying to demonstrate that. And then in the second part, I will try to present some of the work that we're doing that probes whether these models are in good alignment with observations of certain processes that are really important, in particular, the cloud feedback. And what we find is that models at either extreme, both at the low end and at the high end, are inconsistent with observations, at least for the cloud feedback, which is a big governor of the climate sensitivity. Before I continue, I just want to acknowledge my co-authors who are listed there on the slide, as well as the support from the Department of Energy. So just to orient you a little bit here, I don't expect you to take in this whole figure, but this is showing the global and annually averaged radiative fluxes over the planet. And what I just want you to focus on is at the top of the atmosphere. So this is the net radiation entering the planet from the sun, so the incoming solar. Again, annually and globally averaged about 340 watts per meter squared. And about a third of that gets reflected away. So 100 of it watts meter squared gets reflected away on average. And on the long wave side of things in the terrestrial infrared, we have a near balance. So 240 watts meter squared is being emitted by the planet to space. And so you can see that those values are roughly in balance, but of course, there is a slight TOA imbalance, top of atmosphere imbalance, a positive imbalance, meaning downwelling radiation. And that's from the fact that carbon dioxide emissions have been increasing over time. And so this value is a little bit larger these days. This is a paper from 2012. This imbalance has actually increased slightly over the interim period. And that's essentially that tiny imbalance between these two large terms is really what's driving the ongoing warming of the planet. I'm just going to allude to something here very briefly, and we'll come back to this later, is that clouds have a really strong lever on the Earth's planetary energy budget. So a large part of this reflected shortwave radiation is is attributable to clouds by nature of the fact that they scatter incoming sunlight, some of which goes back to space. And similarly, because clouds uh, are essentially colder than the surface of the planet, they also emit less radiation to space, which gives them a kind of a greenhouse effect, essentially. So this is a cooling effect from the presence of clouds, and this is a smaller warming effect from the greenhouse effect of clouds. And how these two effects change is a big uncertainty in our future projections of warming. So in the mean state, clouds cool the planet by about 20 watts per meter squared, averaged over the planet. But how that balance will change in the future is a big open question. So I'd like you to consider kind of a hypothetical situation where greenhouse gases are abruptly changed. Say we double or quadruple them and then hold them fixed in time. How that would affect the planetary energy balance. Very immediately upon that quadrupling, there would be a large imbalance in the planetary energy budget, with a lot more radiation coming into the planet than leaving, because you added a greenhouse gas to the atmosphere. That warming induced by the greenhouse gases would cause the planet to warm. And in so doing, a warmer planet emits more to space just by nature of the Planck response. And so that would slowly but surely restore the planet to energy balance as it warms to come into a new equilibrium with this changed concentration of greenhouse gases. And so over many thousands of years, actually, as the oceans and land warm, you would eventually come back to a new equilibrium state with this new elevated level of CO2, where the net top of atmosphere radiation balance has come back to being in balance. And that equilibrium temperature change is something that we call the equilibrium climate sensitivity. And this is an important variable in climate research. So let's just assign some names to these terms here. So this immediate imbalance that you have as you quadruple CO2 is what we call the forcing. The net top of atmosphere radiation defined positive downward is, I'll call it R. TOA is the top of atmosphere, so it's the planetary energy imbalance. And then global temperature, I'll just represent with T. And we can relate all of these things to each other with a simple equation. So the radiation anomaly at the top of the atmosphere is given by the radiative forcing plus a response. And this response we typically write as the product of lambda and temperature, lambda being the radiative feedback, or you can think of it as kind of a radiative damping of the warming. So if we have a positive radiative forcing from CO2, the planet will warm, and that warming will essentially allow the planet to restore itself to equilibrium. So this is a radiative damping. This is a negative term. So for every Kelvin of planetary warming, more radiation is lost to space, eventually bringing this back into balance. So as I mentioned, the equilibrium climate sensitivity, or ECS, you can derive by just solving this equation for when R goes to 0. And so when R goes to 0, you have the climate sensitivity being the forcing due to a doubling of CO2 divided by this radiative feedback or radiative damping parameter. And we can diagnose all three of these things, the forcing, the feedback, and the climate sensitivity, by scattering the radiation, the net top of atmosphere radiation anomaly against the temperature anomaly in these abrupt 4x CO2 experiments that are conducted. This was an approach that was pioneered by Jonathan Gregory in 2004. So I'll just show you how we typically do this. So we plot the net top of atmosphere radiation anomaly against the surface temperature anomaly for abrupt quadrupling experiments. And so I'll plot here annually and globally average values over time for a 150-year experiment. So your first point here is the first year after quadrupling. And so there's a large top of atmosphere energy imbalance with a lot of planetary heating. And as time goes on and as the planet warms and the planet radiates heat to space, this net top of atmosphere radiation imbalance starts to approach 0. But again, this will take literally millennia to return to 0. But we don't, of course, have that kind of computational luxury to run all these models out to zero, top of atmosphere energy imbalance. So what we typically do is estimate a lot of these things just with these 150 points. So essentially by fitting a line, an ordinary least squares linear regression to these points. And so the y-intercept would give us an estimate of the radiative forcing from CO2. In this case, I'm looking at a doubling experiment. So in this case, the intercept is a little bit less than 4 watts per meter squared per Kelvin, or excuse me, watts per meter squared. The slope of the fit is the radiative damping or the feedback parameter. And then the x-intercept gives you the equilibrium climate sensitivity, which in this model is a pretty sensitive model with a value of about 5.6 Kelvin. Now, there's a whole body of literature and a whole kind of cottage industry of people that are interested in deviations from linearity here. And it's a really interesting subject, and it's become pretty hot lately to study this. But that's a very useful area of study. But here, for this purposes of this talk, I will be only talking about this single assumption of a single linear time invariant and temperature invariant slope that characterizes the response of the climate to forcing. So these are often referred to as Gregory plots in honor of Jonathan Gregory, who first came up with the idea of plotting things this way. And these are commonly used in the community for estimating forcing feedback and climate sensitivity. So it's generally helpful to break down this lambda, this net radiative damping, into components rather than just looking at the total. And so the way we do this is to break it down as so. And we can think of feedbacks basically being a Taylor expansion of radiation on temperature. So it's really the rate of change of the radiation imbalance with global mean temperature, which we can express as the product of the sensitivity of radiation to individual fields like temperature, humidity, surface albedo, clouds, multiplied by the change in those fields with warming. So we can kind of linearize it in this way, and that's a pretty accurate way of diagnosing the system. These terms here are known as radiative kernels, or at least the technique that is commonly used is to use radiative kernels, where these sensitivities are computed once, in a given climate model, and then they can be used across climate models to assess the feedback. So there's not a ton of uncertainty in these terms. It's really just radiation and how that depends on the state of the climate. So the way that these are computed is by feeding a radiative transfer model, atmospheric temperature, water vapor, clouds, et cetera, and then also giving it tiny perturbations on those fields. And you can estimate how that has changed, or you can calculate how that changes the top of atmosphere radiation. And so that gives you a kernel that you can then apply across models or even to observations of these changes in the climate state with warming. And it allows you to compute the feedback. So the kernels would be expressed as watts per meter squared per percent change of water vapor, or watts per meter squared per Kelvin of warming in a given atmospheric layer. And then that would get multiplied by the change in those quantities with warming to give you the net radiative response. And then you can integrate those over the depth of the atmosphere and globally to compute a global feedback. So this is a very common approach that we use in climate to compute these feedbacks. So if you imagine a climate that didn't really have anything interesting going on, as the planet warmed, it was sort of just a rock in space. And so, and all you had was kind of the basic Planck response. It would be kind of boring, and you'd have a really strong radiative damping of something like 3 watts per meter squared per Kelvin. So a warmer planet emits more to space. That's your basic Planck response. Often that's not considered a feedback because it's just the basic response of the system. But some people like to just consider that the Planck feedback. It's just terminology, really. But it's by far the strongest term in the decomposition. It's the strongest negative feedback that allows for a stable climate. So the other feedbacks, really what they're doing are modulating the strength of this very strong negative feedback. So we can kind of add them on cumulatively to get back to the total net feedback. So for example, a warmer planet is going to have less snow and sea ice. These are highly reflective surfaces. So as they go away, you get more warming as the planet gets darker. So that would further limit this strong radiative damping, and you'd have a slightly weaker radiative damping because you've now added on this positive feedback from melting cryosphere. Similarly, water vapor increases as the temperature of the atmosphere warms. Um, and this is because the atmosphere really likes to maintain constant relative humidity. That means that as it warms, the water vapor content actually goes up exponentially. Water vapor itself is a really strong greenhouse gas, so this is really strengthening the greenhouse effect as the planet warms. So again, that's further weakening this strong radiative damping that's there solely due to Planck. And so now you've got a slope that's more like this when you include that effect. Another feedback that's prominent in climate models is what we call the lapse rate feedback. This is the tendency for warming in the atmosphere to not be vertically uniform. So the warming tends to be kind of top heavy. So the upper reaches of the troposphere, kind of the upper levels of the area where clouds form, where the weather is, warms more than near the surface. And that means that for a given amount of warming, you'll actually get more radiation emitted to space than if the warming was vertically uniform. It allows for the planet to shed heat more readily than if warming was uniform. So this is a negative feedback. And so that, the way I've drawn it, it now brings this slope back a little bit more strongly towards the Planck response. So this is a negative feedback. These two feedbacks are actually highly correlated, so they're often combined into a single feedback. They're related to very similar processes, but just with opposite sign. And then finally, you have clouds, and this has always been kind of a holy grail, so to speak, in which direction clouds will go. The way I've drawn it here is a positive feedback. So again, further weakening the radiative damping. But that's not necessarily the case. Some models show a negative feedback from clouds, meaning that they dampen warming. And so that's how you get back to this total response, is through considering the sum of all these different feedback mechanisms. So we can do this across models. So here, I don't expect you to take in this graph. I'm just showing you that you can do this type of analysis for climate models that have been submitted to this archive, which we call CMIP6. This is the Coupled Model Intercomparison Project. So models from all around the world conduct, essentially the exact same experiment so that we can systematically compare them to each other. And they do these regularly. So this is now on its 6th iteration. So there's been 5 intercomparison projects prior to this. And so we can compare these across generations to see how models are changing and how their sensitivities are changing. In the first part of this talk, I'll be comparing the CMIP6 models that are shown here. There's 47 of them to their predecessors in CMIP5. So you can see that this kind of linear assumption works pretty well across models, that there's not a ton of curvature in these plots, and that we're capturing kind of the first order effect by taking a linear approach. And as I mentioned, there's a lot of people working on the higher order aspects of these changes with time. So if we look at the climate sensitivities diagnosed exactly in this way, so again, the climate sensitivity you can diagnose just from the intercept, the x-intercept here in each of these. So I've sorted these in order of climate sensitivity from the lowest sensitivity moving forward to the highest climate sensitivity, which happens to be from your neighbors in the Canadian Climate Model Center. They have the highest climate sensitivity model in the latest go around. And the Russians have the lowest. These are 2 models from the Russian group with the lowest climate sensitivity. I should mention that there's models here from all over the world. So Norwegians, United States, France, a bunch of other United States, UK Met Office, Australia. So we've got models all over the world that are doing these experiments. So again, the x-intercept here is your climate sensitivity, and that's plotted here in the histogram. So the orange histogram bars are from CMIP6, the latest models, and the gray is from their predecessor models in CMIP5. And what I'm showing here is the mean and the 66% range and the 5 to 95% range across models. And so the mean has gone up pretty considerably by about a half a degree in CMIP6, and this has received a lot of attention. The spread has also gone up pretty significantly especially on the high end. So not only has the lower end come down slightly, the two Russian models that used to be here are now here, but now we've got a whole bunch of models that have very high climate sensitivities, and that's widened the distribution in addition to pushing it on average to be higher values. I should note that the Intergovernmental Panel on Climate Change, which is kind of this scientific body that regularly assesses the state of the science of climate, they have a likely range which has been largely unchanged through all of its 5 reports, and really for the last 4 decades essentially has been stuck around 1.5 to 4.5 degrees of climate sensitivity. And what we see in these latest models is that we've now got a huge number of them that are outside of this range, so at the high end. And I just color coded these here as the wolf pack, those models that have climate sensitivities above 4.5 degrees Celsius. So this got a lot of attention when this study came out. I guess it was last year around this time, that the latest and greatest climate models are showing really large sensitivities, implying that maybe the world is in store for even greater warming than was anticipated prior. And so that's really a motivation for looking at whether we believe these high sensitivity models. But first, I want to just establish what's causing these higher climate sensitivities. And of course, based on my motivation, you can imagine that it's relevant to feedbacks. So the climate sensitivity, here's the equation here, depends on the forcing and the feedback. So it's linearly proportional to the forcing and inversely proportional to this radiative damping. So if you just plot these against each other, here's the forcing, the effective radiative forcing, here's the feedback or the radiative damping. I've overlain contours of climate sensitivity. So generally the climate sensitivity increases with weaker radiative damping or a system that's characterized by more positive feedbacks. And it's also slightly sensitive to the strength of the radiative forcing. So if you give if the doubling of CO2 gives a stronger push, you'll have a larger climate sensitivity. But it's really more strongly dependent on the radiative feedback or the radiative damping. So let's just plot the models in this space. So the CMIP5 models are the blue circles, and the CMIP6 models are color-coded with this designation that I gave on the previous slide. And what you see, let's just focus on these really high climate sensitivity models. They're all characterized by very weak radiative damping. So they have, you can say that they have strong positive feedbacks that are really weakening the Planck response. So it's very hard for them to radiatively damp the perturbation that's applied from doubling the CO2. There's some role for increased forcing as well in the latest models, but by far the reason for the larger climate sensitivity in the latest models is the fact that there's a large population of them now that have very weak radiative damping or strong positive feedbacks. So as I mentioned, we can break down these feedbacks into the different components. So here's our very strong damping feedback from the Planck response. This is a slightly different version of the Planck response than what I was talking about earlier. It's one that assumes constant relative humidity. So instead of it being a value of -3, it's something more like -2. And so here's your Planck response, which is by far the strongest damping feedback. This is our lapse rate feedback, our feedback due to water vapor changes, so changes in relative humidity. These are obviously very close to 0. The surface albedo feedback, this is positive, and it's related to the melt back of snow and sea ice. And so if you look at these 4 feedbacks, you see that there's been essentially no movement from the previous set of models to the current. Whereas if you look at the cloud feedback, which again has all this intermodal spread, that's where you see this subtle shift towards more positive feedbacks in the latest models. So largest intermodal spread, and it's the one feedback that has shown a movement from the previous set of models. We can break this down into a shortwave component and a longwave component. As I mentioned at the beginning of the talk, clouds reflect solar radiation to space, but they also act as a greenhouse effect, essentially as a blanket. These two effects tend to oppose each other, but it's the shortwave that wins out. And so we've now got the shortwave feedback having shifted towards more positive values. And this is really the main reason that the climate sensitivity has increased in CMIP6. Just to hammer this home, in case it's not obvious what I'm talking about, this is what the planet looks like And so if you compare that to a planet with no clouds, it's much darker. So obviously climate models aren't totally wiping away clouds, but they're essentially going in that direction where you have a planet that's highly reflective and you're moving towards one that's slightly less reflective. So that, and this is occurring per unit of global warming. So with every degree of warming, you're getting more absorbed shortwave radiation from the reduction in cloud cover or reflectivity. So the warming essentially begets more warming from the cloud changes. And this effect has strengthened in the latest models. So we now have a lot of sophisticated techniques for further diagnosing the cloud feedback. We can look at more than just what is the total cloud feedback, and we can look at more than just shortwave versus longwave. We can actually do breakdowns by the type of cloud. So I like to separate things by low-level clouds and high-level clouds. So you can think of low-level clouds as kind of your stratus, your stratiform, low-level clouds that don't have very high cloud tops, to be distinguished from things like cirrus or the tops of very high clouds that you might see in like a frontal system. Low clouds tend to have a lot of leverage on the Earth's radiation budget because they don't really have these counteracting effects of shortwave and longwave. They're so low near the surface that they don't really have much of a greenhouse effect because they're emitting to space almost similar to the surface. There's not much of a contrast between what they emit at and what the planet would emit at if they weren't there, but they're still bright. So they have a really strong shortwave effect and not much of a longwave effect to counter that. So that's why low-level clouds have a really strong leverage on the Earth's planetary budget. And so that's where all the action is actually. And going from CMIP 5 to CMIP 6, we see a large and statistically significant increase in the mean feedback from low-level clouds. And again, as I mentioned, this is mainly from the shortwave. There's very little change. There's very little effect from the longwave part of the spectrum. Through other techniques, we can break this down even further. We can break this down into asking, well, how much of that is from the aerial extent of clouds versus how much is from the albedo or the reflectivity of clouds, how much they scatter, independent of how much aerial coverage they have. And so that's shown here. This is the low-level cloud amount portion of the low-level shortwave cloud feedback. And so that feedback has gotten stronger. So reductions in low-level cloud amount are stronger, giving more of a shortwave heating effect. And if we look at the scattering effect, it's similar. That's also going in the same direction. So whereas in the last generation of models, on average, the clouds were getting brighter and reflecting more sunlight to space, the average feedback now from low-level clouds is actually positive, meaning that their opacity or their ability to reflect sunlight to space is actually getting weaker with warming. So both of these processes are going in the same direction. We can further break this down by area. So this isn't just a global mean quantity. It's really, you have essentially a map of these feedbacks. They operate differently in different regimes. So here I just broke this down by the tropics. So equatorward of 30 degrees latitude and extratropics, poleward of 30 degrees latitude. And you can see that, again, all the action is in the extratropics. There's been basically no movement at all in the tropics for both the amount and the scattering feedback. And all of the action towards stronger positive feedback is coming from the extratropical latitudes. And in fact, this feedback has switched signs on average from being negative to being positive in the latest models. So here I just show a zonal mean plot. So you take the map and you average across all longitudes, and then you plot it as a function of latitude, or in this case, the sine of latitude, so that it's kind of giving you the right visual of the area represented by each latitude. CMIP 5 in blue, the old generation, and CMIP 6, the latest generation, in orange. And then I show their difference in black. And it's solid where the difference is statistically significant. So again, in the tropics, there's really been no movement on average. The models have about the same feedback strength. It's positive, but it hasn't changed much. In the extratropics, in the old models, we had this kind of dipole, a positive feedback in kind of the equatorward side of the mid-latitudes, and then it transitioned pretty strongly to a negative feedback where clouds were getting optically thicker and more extensive. And what we see in CMIP 6 is that this has just all kind of shifted upwards in the extratropics, most dramatically here in the Southern Ocean. But you can also see that it's occurred as well in the Northern Hemisphere. Um, this was actually not entirely surprising to us, as we saw um, studies that came out prior to CMIP 6 that tried to improve cloud phase representation in models. As you improve that, you actually tend to get more positive feedbacks at higher latitudes. And I'm pretty sure Jen Kay spoke about this last week in the seminar. She was amongst a couple of the people who first pioneered the idea of fixing this well-known bias in extratropical clouds where they have too little water and too much ice. And when you fix that bias, you tend to strongly reduce this negative feedback. And so that was shown with kind of single modeling experiments. And it seems like there was a desire to do this more broadly across the latest generation of models, and that has caused them now to have this stronger positive feedback at middle and high latitudes. The idea here regarding the bias is that if your model has too much ice to begin with, it's going to have a really large transition from ice to liquid as the planet warms. And for the same amount of water, a liquid cloud reflects a lot more radiation to space than an ice cloud. So this huge transition from a lot of ice to a lot of liquid was giving rise to a very strong negative feedback, a very strong dampening feedback. And so if you fix that bias and you have enough water to begin with, and you don't have a lot of ice necessarily to begin with, you're not going to have that big transition from ice to liquid with warming. And so that generally wipes out this strong negative feedback in the high latitudes. And so that seems to be what we're seeing. So qualitatively, that's actually an improvement. We actually think that that is more in line with observations to not have such a strong negative feedback at these latitudes. So I hope that was fairly convincing that cloud feedbacks are the reason that we have higher climate sensitivity in the latest models relative to their predecessors. So now we'd like to ask, well, what do observations say? What can we bring them to bear on these models to try to, better understand whether this is a plausible future that we should be anticipating? Specifically, I'll be talking about low clouds because they have a lot of leverage, as I mentioned. I'll be highlighting here work that was led by two early career scientists, Ryan Scott, who's now at NASA Langley, and Tim Myers, who's my postdoc here at Lawrence Livermore. So they led the remainder of this work. So just to remind you, the climate sensitivity is really well explained. The intermodal spread is well explained by the net cloud feedback in models. So if you've got a strong positive cloud feedback, you're going to have a large climate sensitivity. And you can extend that even further to be specifically the shortwave low level cloud feedback. So the models that lose their low clouds more strongly have a stronger positive, have a larger climate sensitivity. So that really motivates us to focus on the low level cloud feedback. The way that we like to do this is to have a look at cloud changes through the lens of what we call controlling factors. So this is the meteorology that controls low level clouds. So what you're seeing here is how we kind of conceptualize the idea of a low cloud feedback. This term here is essentially the low level cloud feedback. It's the change in radiation that's attributable to low clouds per degree of warming. So this is the low level cloud feedback. And we can write this kind of similar to how we wrote the feedback earlier as the sensitivity of low cloud radiative effect to various cloud controlling factors multiplied by how those factors change with warming. So there's a large body of literature that has looked into what are the low cloud controlling factors. So what is the meteorology that governs low cloud properties? And the two most important are sea surface temperature, that's SST, and something that we call inversion strength. And I'll explain that a little bit better on the next slide. But there are several other terms as well, like temperature advection near the surface, the vertical motion of air in the troposphere, wind speed. There's a number of parameters that really matter for governing low cloud properties. So this is how we kind of conceptualize the problem. So to give you a sense of what these cloud controlling factors are, as I mentioned, the two most important are sea surface temperature and estimated inversion strength. So the atmosphere where you have low-level clouds is generally pretty cool and moist, and it's capped by what we call an inversion. So the temperature structure is one where it's fairly constant with height, and then there's a sharp kind of cap or a lid that keeps the low-level atmosphere very cool and moist, and it essentially serves as a barrier to mixing with very dry air above. So the air above cloud is generally extremely dry and has a higher potential temperature than the air that's in the boundary layer. And so the way you'd want to maintain clouds or to have more clouds is to keep this barrier as strong as possible between mixing of dry air above with the moist air below that could potentially desiccate the cloud. So a stronger inversion is really good at keeping that barrier, keeping the dry air above from mixing into the moist air below. And similarly, having cold surface temperature is helpful in the same regard in preventing this strong mixing of dry air that could potentially desiccate the low cloud. So in the global warming case, we tend to have obviously higher SSTs in the regions of low clouds. And so that is a process that would tend to decrease low clouds. And similarly, the inversion strength, depending on how that changes, that could have a big impact on low-level cloud cover. So these are the two most important parameters that we find governing the response of low-level clouds to warming. So we're going to look at cloud changes through the lens of cloud controlling factors. As I mentioned, this is the feedback and this is the framework we're using. So global climate models are in reasonably good agreement about these kind of large scale meteorological changes, how SST and inversion strength will change. And in a practical sense, this is all we have to work with if we want to try to predict how clouds will change in the future. We'll use the climate model responses of the environmental parameters. In contrast, the thing that we don't trust models for is the sensitivity of cloud properties to these meteorological controls, because this is essentially governed by processes that models just simply can't simulate. They are occurring at scales that are below what a model can resolve. So that's really where all the intermodel spread comes from in the cloud feedback. So the idea here is that, well, if we don't trust them, let's swap them out with things that we do trust, which is actually the observed sensitivity of low clouds to their meteorological controls. So these are things that models can't resolve, so we swap them out with things that we observe. These are the processes that models can resolve pretty well and don't really disagree much on, so we use the models here. So it's kind of a hybrid approach to try to constrain with observations the low-level cloud response to warming. Okay, so as I said, we derive this from satellite observations, and we take this from climate model simulations. There's details here that I don't think are super relevant, but I can talk more to later if anybody has questions as to how you derive these things from observations. So this is what you get. This is just from one satellite product. It's called the MODIS satellite. And it's over roughly the last 20 years. So we use interannual variability in the satellite record. And that gives us these sensitivities of how radiation due to low clouds responds to sea surface temperature, estimated inversion strength, and these other parameters that are also relevant in terms of getting the right coefficients, but in terms of the future warming, they don't end up playing a big role. So the sign here, just to be clear, positive means planetary heating due to reduced low cloud coverage or optical depth. So it's maybe easiest to think about this in terms of the inversion strength. So these terms are all pretty much negative, meaning that if you strengthen the inversion locally, you're going to end up with more low-level clouds. And that's going to be a cooling effect on the planet because those low clouds reflect more radiation to space. So estimated inversion strength is a really powerful control on low-level clouds and the radiation of the planet, essentially. These are all expressed in units of watts per meter squared per standard deviation. So that way we can plot them all, even though they have different units. Sea surface temperature is in units of degrees, whereas relative humidity is in percent. So these are all standardized by their interannual variations to put them in per standard deviation units. So as I mentioned, these two terms are really the two important. And so we can now scale these with the change in SST and inversion strength with warming, which we get from the climate models. So here's the response of these to 4 times CO2, again, in standard deviation per unit global warming. So the SSTs obviously warm everywhere. And when we convolve these with the sensitivities that you saw in the previous slide, you get something like this. So really strong positive response in these kind of stratocumulus regimes that are off the west coast of continents. Um, and then we can do the same thing with the EIS, the estimated inversion strength part of this, and we get a map like this. So we can do this for all of the different cloud controlling factors and sum them up to get essentially an observationally constrained map of the low cloud feedback. That's a little bit hard to take in all at once. So what we like to do is to break this down into regimes, because different cloud regimes behaved in different ways, as you can kind of see here with the SST. Stratocumulus behaves differently from the clouds that are farther offshore, which are a little bit more what you might think of as like cumulus, like kind of popcorn, cauliflower looking clouds, as opposed to these sheets of stratocumulus. So what we do is we break these down into regimes. So again, your stratocumulus kind of hugs the coast. You've got your trade cumulus regime, which is this cauliflower type. You have regions of tropical large-scale ascent where you tend to have more like deep convective thunderstorm type systems, but they also have low-level clouds underneath them. And then our mid-latitude clouds, which are related to storm systems like mid-latitude cyclones. So we do this breakdown in these different regimes. And here's what we get. So this is the regime average marine low cloud feedbacks for stratocumulus, trade cumulus, tropical ascent, and mid-latitude regions. These are 4 different satellite data products that we have and we've done the analysis on. And so these are the estimates that we get. The best estimates are shown with the symbol, and then we have 90% confidence intervals on this. And this uncertainty reflects uncertainty in the various regression coefficients. So how sensitive is the cloud to the meteorology? And that gets propagated through as we add them up, as well as the uncertainty in the responses to warming. So that's the uncertainty that's coming from the model responses. So what we see here is a positive feedback implied by the observations in stratocumulus regions, as well as in the mid-latitudes. And in contrast, the feedback from these other regimes like trade cumulus and tropical ascent are quite small and close to 0. Now we can compare this with what models show. So here I'm showing the CMIP5. This is the previous generation of models where they lie in this same framework. So we do the exact same analysis with models using their cloud controlling factors and ask what their feedbacks are. So we can see that the GCMs, the models, underestimate fairly strongly the stratocumulus feedback as well as the mid-latitude feedback. But they tend to have feedbacks that are too positive in the trade cumulus and tropical ascent region. So it's kind of a mixed bag of compensations in the models where they don't quite capture the observed sensitivities right. We now show the CMIP6 models. These are the latest models. There's basically been no movement anywhere but this mid-latitude feedback, which, as I mentioned earlier in the CMIP5 versus CMIP6 results, these have become much more positive. And so we're seeing that here as well, switching from a small negative feedback on average to a moderately positive feedback that agrees quite well actually with the observations. So in order to get to a near global feedback, we need to scale these areas, scale these regions by their fractional area, which is represented by the percentage, the parenthetical percentages here. So the stratocumulus, it has a huge feedback, but it's a tiny area of the globe. So when you scale it, these things tend to be a bit more equable, I guess you might say. But what that allows us to do then is to get, a near global 60 south to 60 north marine low cloud feedback estimate from observations. And we combine these semi-independent estimates from the 4 different satellite products into one kind of meta estimate, which is a positive low-level cloud feedback of 0.2 plus or minus 0.12 watts per meter squared per Kelvin. So let's just compare this with the models again. As I mentioned, the feedback has gotten larger in CMIP 6 relative to CMIP 5 because of the mid-latitude. There's been a lot of movement in the mid-latitudes, whereas everything else has mostly stayed fixed. We now have a lot of models that are way up here on the high end, outside of where the observations say you should be. And as you might expect, these are all models that are part of the wolf pack, very high climate sensitivity models. So although there was a lot of attention given to this mid-latitude feedback being much more positive, and people are questioning whether that's actually right, by this analysis, the models are in much better agreement now on average with observations. So we think that that's actually a movement in the right direction on average. There's still a couple of outliers there, of course, but the general tendency is one towards an improvement. In contrast, there has been a persistent bias in the trade cumulus feedback as being too positive, and that remains the case in CMIP 6. So we need to, keep our eye on these low latitude regions that have a broad area, because they remain biased in the latest models and are probably a big part of the reason why the feedback is too strong in many of these models. I'm going to skip this just in the interest of time, but the point here is that we can derive an updated estimate of climate sensitivity that goes beyond just looking at climate models, but also includes evidence from the paleoclimate record, the instrumental record, and these sorts of process level studies of feedbacks to derive kind of a Bayesian, put them together in a Bayesian framework to get a posterior estimate of ECS. But I can come back to that if there are questions. So just to conclude, the mean and intermodal spread in climate sensitivity has increased markedly in the latest models relative to their predecessors. The largest contributor to this is stronger low-level cloud feedbacks from stronger decreases in low cloud coverage and albedo in the exotropics. We think that this is actually an improvement. It's related to the physical representation of clouds, and in particular, getting the right mix of liquid and ice to begin with has improved this feedback. So to get back to the question at the beginning of the talk, whether we trust these high climate sensitivity models, um, there seems to be indications that we shouldn't trust them. So these extreme climate sensitivities above say 4 degrees, or even those that are below 2, are largely inconsistent with our observational constraints on the near global marine low cloud feedback. And so we think future work should continue to look at individual cloud feedbacks, to interrogate them against other evidence from very high resolution modeling and from observational analyses, as well as theory, to try to continue to hone in on what models are doing wrong that lead them to get feedbacks that are kind of outside the range of what is supported by other evidence. So I really appreciate the invitation to talk again, and I'm happy to take any questions. Thanks.